My name is Alexander Panov. I am from Skobeltsyn Institute of Nuclear Physics, Moscow, Russia. My talk will be about TAIGA-HiSCORE Cherenkov array in OSETI program. This is TAIGA collaboration. There are a number of universities and institutes from Russia, Germany, Italy, and Romania. And I would like to start my talk with some words about cosmic rays again. Cosmic rays are charged particles with very high energies, and there are also high energy gamma quanta. When cosmic rays or gamma quanta interact with the atmosphere, they produce a flux of secondary charged particles, this one, and optical Cherenkov's photons. And it is just extended eye shower, ES. To detect charged particles, some charged particle detectors may be used. And to detect Cherenkov's light, various optical detectors and telescopes. This is the astrophysical complex TAIGA is located near the Baikal Lake in the Tunka Valley and designed to study cosmic ray physics and for high energy gamma ray astronomy with using of ES. There are a number of different arrays and telescopes here. Among others, there is a wide-angle TAIGA-HiSCORE array to detect Cherenkov's light from ES, and there are also TAIGA-IACT telescopes that work together with a HiSCORE array. This is a general view to one optical station of TAIGA-HiSCORE array, and this is TAIGA-IACT telescope. The HiSCORE array currently consists of 120 wide-angle optical stations. The size of the array is greater than 1 square kilometer. Here you can also see the positions of IACT telescopes. Shown in this slide are the parameters of the HiSCORE optical station. The one optical station of HiSCORE array has a very large field of view. It is 0.6 teradians. In other words, it is 2000 square degrees, and it is 1/10 of the whole sky. The threshold flux of the one optical station is 3000 green photons per square meter per 10 nanoseconds. The signal duration that we can reasonably measure is from 5 nanoseconds to 100 nanoseconds now, and the last value may be tuned. The digitization step is 0.5 nanoseconds. The main idea of the work is the following. The HiSCORE array can register not only ES events, but also events that could be caused by distant optical nanosecond transients of astrophysical nature. space-time structure of EAS high-score events expected to differ significantly from space-time structure of distant point-like optical events. Therefore, we can search in the high-score data for events of distant optical nanosecond point-like transients. It is very important that no special hardware triggers are required to search for optical transients in the high-score data. All work is performed in a pure accompanying mode without interfering with the main task of the instrument. This slide illustrates this idea. This is a configuration of high-score array in 2018-2019 winter season, the data of which was processed in the present work. You see a typical EAS event, an event from a laser installed on a distant Earth satellite. EAS event typically represented by a compact spot with different amplitudes, different sizes of these circles, different amplitudes, but distant point source is represented by a more flat event with approximately equal amplitudes of different optical stations. What could be a distant optical transient in nanosecond region? Among possible others, it may be a pulse of a distance alliance laser. Therefore, with its very large field of view, the high-score array is a suitable instrument for optical SETI program. What kind of a laser can be detected by the high-score array with these optical thresholds? Here you can see the necessary energetics of the laser in megajoules per 10 nanoseconds, depending on the distance in light years to the lasers, and from laser aperture in the supposition of the best suitable focusing of the laser to the Earth. You can see that these are generally quite moderate instruments in its energetics for all reasonable interstellar distances and reasonable laser apertures. Very large aperture lasers like 1 kilometer are not, of course, single lasers. They are phasing laser arrays, and such devices already exist on Earth. For comparison, you can see the energetics of existing systems in thermonuclear synthesis. This is like 4 megajoules per 2 nanoseconds, 1.5 megajoule per 4 nanoseconds, and these values are quite comparable with the values for expected cosmic lasers. Now, some words about methods. All present work is based on the high-score data of 2018-2019 winter. There were 80 clear nights of observations, or 475 hours, and exposition was 288 steradian hour. The expected signatures of astrophysical optical transients are the following. First, small amplitude spreading among the triggered optical stations in one event. Second, good fit of optical stations response times by an exactly plane optical front. And third, uniform distribution of positions of flashed optical stations upon the surface of the high-score array. In other words, no spot-like distribution like in usual EAS events. In this slide, you can see an idea of the reconstruction method for the directions of sources using the trigger times of different optical stations. The trigger times are measured with some errors, of course. Therefore, we don't expect to fit some plane front to the station times exactly. Instead, we have to find optical front direction by minimization some chi-square-like function of two angle coordinates. This is schematic presentation of plane front. These points are represented by optical stations with different coordinates, and it is two-dimensional simplification of real picture. In this picture, you can see all reconstructed direction in local coordinate system, phi, theta, and in absolute equatorial coordinate system, right accession, declination. We can observe satellites with laser on board. We had 2 times of Calypso satellite observations and 12 times of a space station laser observations. Calypso LiDAR path duration is about 20 nanoseconds. Its altitude is about 700 kilometers. Therefore, Calypso LiDAR pulses is an ideal calibration signal for HiSCORE. As the right panel, you see the detected Calypso tracks with a high-score array, and at the left panel here with the IECT telescope. The precision of reconstruction of the angle coordinates have been estimated from high-score tracks, and it is about 0.05 degrees. And this precision is for near-zenith events where all tracks were detected for satellites. You can see that the structure of satellite events compared to EAS events actually confirms the method to select events from distant optical point cloud sources. This is real satellite events, and this is real EAS. You can see the difference between them. Now I am approaching to the results of the work. Size of event is the maximal distance between triggered stations in this event. It is very important criterion of selection because it is a measure of degree of flatness of event. You can see that flat satellite event have generally greater size than EAS events. In two lower panels, you see the angle distribution for all events with sizes greater than 900 meters. It is seen that in near-zenith region, there are Calypso tracks, these points, but there are no other candidates to optical transients. It is exactly our first result. We found no candidates to optical transients in the near-zenith region here and in the related region of absolute coordinates. But there are a number of events with large zenith angles, events far from zenith, which have great sizes and may look like flat events from optical transients. These are very shallow events that can behave like events of distant point-like sources. We have 511 such events after all season of observations and after applying of all filters. You can see all these events in this slide. The question is, can we search optical transients among such background? The answer is yes, yes, if we will find not single events, but repeaters. Uh, uh, what can we understand under the events in the same point of the sky? It is the following. Coming from one point in the sky means exactly having the same angular coordinates within the arrow bars. Therefore, it is necessary to know the errors in determination of the angular coordinates for events, primary candidates for transients, for the same field of sky, approximately the same field of sky. The errors were calculated by Monte Carlo method for large zenith angle of these events, and the result is the delta phi is equal to 0.03 degrees. I would like to remind that from Calypso data, for near zenith angles, the precision was 0.05 degrees. Calculated value is a bit better than value for near zenith satellite events, but it is not strange. Different regions in the sky may have different precision for angle determination due to different structure of the events. There are some problems with with calculation of these errors, particularly due to non-Gaussian distribution of deviation, but we have final decision. The events considered to be in one point in the sky, if they are in the circle around the center of mass of these events with radius r equal to delta phi to square root of 2, and it is equal to 0.041 degree. With this condition, we found one candidate. This red circle is this candidate. To double repeater, there are exactly 2 points in this circle. But the probability of random simulation by background ES events of one double event calculated by Monte Carlo simulation is not less than 10%, and it is a rather large value. Therefore, we can't insist that the found repeater is a real candidate to distant optical transients. But we actually understand what should be the condition to be confident that the repeater is actual candidate to optical transient. There are a number of such situations. For example, if we have at least one triple event, then the probability of a random simulation of such event by EAS background is very small, 1,000th of persons. Now, the observation time is known. It is 475 hours. The collected exposition also is known. It is 288 steradian hours. And no optical transients were found. Therefore, an approximate upper limit on the rate of events may be established as the following: for events with a flux density of photons greater than 10 to minus 4 ergs per second per square centimeter, and with a duration greater than about 5 nanoseconds, the flux is less than 2 times 10 to minus 3 events per steradian per hour. This value is some bit preliminary, yes. Now we have processed only one season of high-score measurement. There are two seasons. We have the data of these seasons in our hand, but they are not processed yet. What is important that in these two next seasons, the high score array was larger than in the season that was processed. Therefore, the background will be lower, and it is very important. Now, I would like to say only about 2 words about TAIGA-IACT telescopes. We are going to use TAIGA-IACT telescopes for OSETI as well.
I'm sorry, Alexander, we are a little bit over time, so would you mind wrapping up in the next 2 or 3 minutes or so? Thank you very much.
This is to the last slide. Can you?
Okay. Yeah, thank you. Yeah.
Yes. The field of view is rather large. It is 9.6 degrees. The threshold is 50 photons per square meter per 10 nanoseconds, and it is very important. Any special hardware trigger is not required again for OSETI. All work will be done in a pure component mode. Well, this is about the structure of the trigger, but I have to finish my talk. Thank you for attention.